So we're going to get started on this talk, portable scale-out benchmarks for MySQL. That title is actually a bit humble. We're going to be talking about benchmarks for basically any database. One of the things that we'll be focusing on is some tools that we've developed at Continuent to help with scale-out testing that I'd like to introduce you to today and show you some results. My name is Robert Hodges. I'm the CTO for Continuent. I'll talk a little bit about the company in a minute so you see what we do. I've been working on databases specifically for something like 18 years now, and it's a great field. It's a wonderful intellectual problem. I also have this kind of sick interest in testing, so I've done a lot of work in that area, both functional as well as performance testing, and this stuff that we'll be looking at today is one aspect of that work. So here's what we're going to talk about. Do some quick introductions. I've already introduced myself, but I'd like to introduce my company. I'd like to review Scaleout a little bit. I think everybody in this room, I'm sure, if you're a MySQL user, you have a pretty good seat of the pants understanding of Scaleout, but I'm going to back up a little bit and talk about the problem in general as well as some of the technical approaches, because there's actually multiple approaches to solve this problem, and not all of them are used in MySQL. I'm then going to introduce the bristlecone performance testing tools. That's the testing tools that we have, show you how they work. I'm going to give you a few benchmarks, which are really suggestive. I'm not doing, at this point, presenting formal benchmark results that you can say, oh, this is TPCC behavior guaranteed to have so and so many dollars per transaction. These are more suggestive. They just show you how to use the tools. Of course, when our software runs better, we will examine those results quite carefully. So then finally, just a few concluding words. So about Continuent, we style ourselves the leading provider of availability and scaling solutions for open source databases. Been around for quite a while. We've done quite a bit of history in database clustering. We did what we call an in-core cluster called mCluster for MySQL that is actually run right now by the National Weather Service and other places. All the weather reports come off that. Our current product is Unicluster, which is a multi-master database clustering solution. And the way it works is you have a middleware layer that sits in front of your databases, basically funnels the reads to load balances the reads off single databases, sends the writes to all of them. It uses this technique of database virtualization to provide a transparent interface or transparent layer between clients and servers. So this has a number of, the value proposition is sort of multifaceted, but basically it's raise availability, raise scaling, allow people to do online maintenance, and remove the chance of losing data. We do a lot of work in open source. Ultimately, all of our products are based on open source. We build commercial things on top of them. The key thing, the key open source product that we sponsor right now is called Sequoia, which is generic middleware clustering for JDBC. But we have a number of other projects that are related to that. And in fact, I'll discuss the stack because that's kind of relevant to this whole problem of testing that we're going to be discussing. One thing that I want to point out besides bristlecone is this thing called MySQL. That's actually a plant. It's the scientific name of forget-me-not. That is a fast Java proxy that will accept connections from native MySQL clients, turn around and issue JDBC calls. That's a very important part of our architecture. It's actually quite an interesting piece of software. Clustering is pretty advanced stuff. We tend to do a lot of collaboration with people in the research community, trying to sort of remain on the cutting edge. One of the main groups we work with is right now is Portabe. This is out of UMinho at the University of Lisbon. They are actually doing a talk here at this presentation. They have a real interesting pluggable replication architecture that I think is quite significant. But we also work with other people in the research community as well. So I'm going to dive in a little bit and talk about Scaleout. I think that most people understand. I think most people understand the problem quite well. there's this huge motivation to get better availability. So you want to protect yourself from database failures. You want to protect yourself from site failures. You want to be able to operate continuously during upgrades. You also want to scale. So you have peak loads, you have large numbers of writes, you have large numbers of reads. And as we know in the MySQL community, and I think this community has shown really well, one way to address both of those problems simultaneously is just to spread copies over a lot of hosts. There's been, I would say, half the talks that are at this conference mention that in one way or another. So if you have a failure and you lose a copy, you just move to another one. If you have a lot of read traffic, for example, you can distribute them onto the extra copies. You can also, for writes, you can also shard or partition. I'm not actually going to talk about that today, but it's something we're quite interested in. So the big thing about Scaleout, the reason it is so popular, is that it's an incremental approach that allows you to start from a relatively small base and then just incrementally add hardware, add resources to get your capacity, both in terms of availability and scaling, to increase over time. So in fact, when I think about Scaleout, I don't think about it so much as a technical solution, but as an economic model for computing that we're enabling here in the MySQL community. So this is the dream. Increase scalability, increase failover, just by basically multiplying application services as well as databases. The issue with this, though, is that even though that's a great picture and everybody has this in their mind, if it's so great, why don't we have it? Why doesn't it work perfectly? And I think if you went, for example, to Lonnie Taylor's talk yesterday on the availability landscape, you saw that there's all these different kinds of solutions. He was focusing on availability. He had a bunch of different scale-out type solutions. And they all had trade-offs of some kind. And the fact is that this is just a really hard problem. It turns out that creating a set of identical replicas across a set of distributed hosts, distributed processes, is a very hard problem. So, for example, if you're trying to serialize transactions just in middleware, for example, if you have somebody sitting and receiving a bunch of SQL requests, and they're trying to make equivalent copies on a bunch of databases, it turns out the algorithms to do that are not as good as the serialization algorithms inside a database. You also have things like Brewer's conjecture, which is also called the CAP principle. It stands for consistency, availability, and partition tolerance. You can only, there's a theorem that basically says in a distributed environment, you can only have two of those three. So if you think you're going to have network partitions, if you think you want to be totally available, you're going to have to sacrifice consistency of data. And then on top of that, the most promising algorithms in this area often require you to go in and do at least some modifications to the database. So as a result, you tend to get some real approaches. There's some big trade-offs functionally in this stuff. So for example, some approaches don't support PDL well. You obviously have the inconsistent read problem. On databases other than MySQL, you have sequences. These can be very difficult for replication. You have non-deterministic SQL for people who are dealing with MySQL statement replication. You know about this. And you have deadlocks. So the effect is that these approaches tend to be non-transparent. In other words, when you do scale out, there is no simple way that you can create the illusion that you're just going to one single database. And this is important because what it means is if you test as if you were, and do performance as if you were going to a single database, you're sort of missing at least some of the point. And in fact, personally, I think it's not surprising that Scaleout is, in addition to the features built into MySQL, like MySQL replication, I think it's not a surprise that Scaleout is really common in the MySQL community because you have a lot of people using scripted languages like PHP, like Perl, where you can quickly modify the applications to deal with these trade-offs. In addition to the functional trade-offs, of course, there's also some major differences in performance. And that's actually what we want to focus on a little bit more from here on out. So there's basically, as you as you attempt to scale out, there's three very common technologies that one way or another tend to appear, you may, in one form or another, in each of the solutions that you're likely to look at. The first, and by far the most important one, is data replication. So basically making copies, one place or another. Now, you can do this at the disk level, but for now, what we're really concentrating on is doing replication at the database level. So, and there's a couple different variations on this. It's master-master, which means you can basically send your writes to any of your database nodes. Master-slave means it goes to one and it's propagated out. There's also differences in when they're replicated. So, for example, synchronous versus asynchronous. These have performance implications. For example, if you're looking at master-slave, one of the performance questions you have is what is the latency of these slaves? This is a very significant issue. For master-master, one of the performance issues you have is how fast can I do updates? As I mentioned, the serialization algorithms that are used to feed these masters are not as efficient as algorithms inside the database. Another important technology is group communication. So this is not used terribly widely in the MySQL community, but group communication basically is a technology developed, most variations on it would come out of Cornell, and I work from Ken Berman. It basically allows you to keep a bunch of processes in a network in sync. Does two really important things for you. Maintains views, like if you've got a bunch of people, a bunch of processes that constitute a cluster, who's in the cluster, who's crashed, how many members you have, it gives you that information. It also gives you message delivery, because as you're sending, for example, replicating data, it's really important, for example, that everybody receive messages in the same order. Otherwise, you get inconsistent updates. So group communication is important for bottlenecks, or for performance. If you are dealing with a Scaleout solution that uses it, one of the questions you want to ask is, are there bottlenecks because of group communication? For example, to order messages between two hosts, you usually have to send a message, basically have an exchange of messages between the hosts, for example, running around a token ring, or between two hosts. So that gates how fast certain things are going to happen. And then finally, there's proxy. So this MySQL has MySQL proxy. I think they've gotten this, MySQL has gotten religion on this. But basically, whenever you have any sort of layer that virtualizes your databases and deals with things like load balancing for you, deals with things like finding databases that are up, handles failover, you've got a proxy. So questions come up about what is the latency, what is the performance cost that's induced by having that. Let me talk about replication algorithms, just dig a little bit deeper into that. So this, I already talked a little bit about this on the previous slide, but there's really three general ways to do replication, of which in MySQL itself does master-slave replication, and in fact does it very well. So you accept updates as a single master, you send them out to the slaves. As I say, some of the primary performance concerns there are latency of slaves. Another concern you have is the performance hit on the master. And in fact, we'll look at that in detail in just a little bit. There's also an approach called, in the research community, it's called multi-master state machine. This is what we do with our product right now, which is basically, you have a string of updates coming in from a bunch of clients, you order them, and you apply them to a bunch of databases simultaneously. And it uses a state machine principle that everybody gets them in the same order, and the database is started in the same state when you're done, it'll be in the same state as well. So that's another important way to do replication. Performance impacts of that approach are that the update rate in this particular approach tends to be slower than MySQL. So you're going to look at updates, how fast can you do those. You're also going to look at things like, sort of what's overall throughput for things like reads, so on and so forth. And then finally, there's an approach that we have implemented, but is not actually, doesn't exist in the MySQL community right now. That's a certification approach. where you have a bunch of databases that tie together in a cluster. The way that it works is you come in, you do an update, you optimistically execute it on one of your databases, and then you have an algorithm using group communication that goes out and applies it to all the other databases. And they have a process they go through to say, hey, am I breaking serialization? If I am, I'm going to throw it out. If I'm not, then I'm going to apply it. The reason I mention this, even though it doesn't exist yet, as we look at Scaleout and testing approaches, we're thinking about this. This particular approach, the questions you have are how fast can you update, and very importantly, in this particular approach, do you get more deadlocks or aborts? That's one of the side effects of this. So there's actually software out there that we can test. As I say, not much in MySQL. So our goal at Continuent, and the reason I'm going after this so broadly, is that we are looking to create highly reliable, transparent, and easy to deploy solutions to deal with availability and performance. And we want to use the scale-out model. We want to be shared nothing. So basically, use unaltered relational databases like MySQL and economical off-the-shelf hardware. That's the whole point of scale-out. And so we have an architecture that we call Tungsten that is designed to meet that goal. So what we're doing is we're basically using most of those technologies that I just covered in this architecture. We create these things called data services, multiple copies. They basically are like distributed databases. We try and make them look as much like real databases as possible. We use database virtualization, so we're really, really interested in the performance of that. We have middleware layers that do proxy. We are developing, well, we already have the one form of replication. We're working very hard on master-slave replication that works across databases. Again, so these performance issues are very interesting to us. And then we're doing management, which is somewhat less important for this. What we're developing to implement this is a stack. So this basically is a set of technologies. And this kind of comes back to this point that there's these different approaches, and for any given problem, one is appropriate but not another. We basically have a stack that includes connectors, that's the proxy, includes the multi-master synchronous replication, async replication, management, and then very important, this bristlecone, because I think if you're attacking this problem, it's not enough to have a bunch of technology pieces that implement it. You also have to think about performance and, well, testing in general, and particularly performance testing. So this bristlecone that I'll be talking about in a minute is part of the stack. Oh, and here's a pretty picture of what the data services will look like. This is something we're implementing. I didn't talk about it. So anyway, let's get into bristlecone and talk about performance testing. So as you're looking at performance testing, you have to have a strategy. And one of the reasons I covered the technologies in QA in general, you always want to be clear about what you test. What is the thing you're testing? What are its potential weak points? What are the risks? So the first thing is to run appropriate tests. So you can use mixed load tests to do overall throughput and scaling. But then you also, when you're doing scale-out, it's really, really important to do what we call micro benchmarks, where you actually zero in on a very, very specific thing like lead latency, and then test it a bunch of different ways. Like test it as you scale from, say, 1 client to 100. Test it as you scale from 100 rows returned up to 10,000 rows returned. So you want to be able to do these micro benchmarks very systematically, because they, first of all, give you costs of certain operations if you're trying to model things or sort of think about the capacity, reason about capacity. The other thing is when you have problems with performance, they allow you to zero in on where the problems happen. Another thing is to use appropriate workloads. And what we find, and I think what you often hear from people outside of the MySQL community is they're just going to roll into TPCC and check out performance. Well, if you're using master-slave replication with MySQL, that's a bit silly. That architecture is not designed for that kind of OLTP profile. So what you want to do is make sure that you can dial up the, for example, the level of reads and test a very read-intensive load, like 97% reads. You want to cover the key issues, and these are some of them: read latency through proxies, read and write scaling, slave latency, bottlenecks from your various types of communications, and then you want to look for aborts and deadlocks. And you want to generate sufficient load in the right places. So I think of, you can, in a previous version of this talk, I was thinking of putting up a picture of a database and just thinking about, well, what are all the places we can go poke and make it fail? Things like the buffer cache, things like testing scale, large data sets, so on and so forth. These are all really important. Another thing in the MySQL community, because there's such heavy use of database replication, is to watch data types. So BLOBs and text often have these amazing hits. They cause these amazing hits on performance when they're running through the replication mechanism, for example. So all kinds of things. So we have this problem, and we have our own software. We have this stack that we're developing, or that we have partially developed already. So we needed to have a benchmarking mechanism as part of that. So we created Bristlecon. And the goal was to create portable tests that cover the basic performance issues. So for example, you can use them just to test an ordinary database, and we do that sometimes to answer customer questions, but also to go after these scale-out issues. It's really important to have them work generically across database types. Most people in this room are probably mostly focused on MySQL. But in fact, we like to be able to compare across databases. We like to be able to have a set of tests where you develop them for one database and there's no effort to run them somewhere else. And then finally, when something is very easy to extend and add. So we have three general types of tests, which I'd like to have. We've basically got 2 out of 3 right now. We have a load test called Evaluator. We don't have batch transaction loading. This is something that I feel kind of bad about, but we'll get to it. When you're testing things and replicates, master-slave replication, again, a good example. Really important not to forget your batch loads, because you may do fine when you have, say 100 updates per second flowing through the system, but you may have batch loads at night where you load in too many records. So a question for you is how fast is that running through the system? We don't have any automation for that right now, other than running MySQL dump and piping it back in through MySQL. And then finally, we have the micro benchmarks. And in fact, the micro benchmarks is where most of our focus has been today. So let me talk about the first tool. This is the mixed load testing. It's called Evaluator. One thing I should say, I didn't mention this, but these tools are all written in Java. There's a couple reasons for that. One is that, well, we love Java, so we write most of our stuff in it. But there's another really important reason for testing, and particularly if you want portability, and that is that Java has an API which is standard across databases. Unless I'm greatly mistaken, I think in the commonly used scripting languages, the only scripting language that can do that is Perl, with the Perl API. It is, and the other thing about the Java API, which is shared by the DBI and Perl, is that it can do prepared statements. It can basically, and for many databases, it doesn't make a lot of sense to do certain tests if you can't do prepared statements. So this is a Java tool. It generates mixed load. Oops, I left the Postgres thing in. pgbench, that's actually a TPCD implementation that Postgres has really greatly programmed. Basically, it's cross-database, so you can use it on any database. You can vary the different types of updates you have, so insert, update, and delete, as well as select. We have a default select statement that doesn't look very harmful, but turns out to actually bash the daylights out of a lot of databases. It's just basically a table in the middle joined to 2 other tables. Basically, the 10 and 100 numbers and the 90 and 200 numbers, these are just random. We insert random values there. And what this does is it generates typically a lot of CPU load on the databases. We'll see an example of that in a second. You can actually choose lighter weight queries. There's an option to pick one that just does a key lookup. And then we can generate all kinds of output. And I'll show you an example of that in a second. So the configuration file looks like the following. So this is testing for Postgres, but in fact you can just as easily, I should have substituted in the MySQL one. But basically, the only thing that you change is the name of the database driver and your connection information. All the rest of the stuff is totally standard. So this is a test that does a thread count. It's going to generate 100 clients. They're going to have 500 milliseconds think time on them. We have the percentages of our updates, deletes, and inserts. So this is going to generate a 10% write load on the system, of which 7% are updates, 1% deletes, 2% inserts. We're going to use a medium weight query, so that's going to do an aggregate. That's actually not quite as heavy as that query I just showed you. And then one nice feature is we have, another nice feature is we have a ramp up, so that you can say, hey, I want to step this up. And what I'm going to do is every 5 seconds, I'm going to ramp up by 10 clients until I hit the top number. The amount of time, let's see, test duration is up at the top, that's 600 seconds. That's useful for doing talks like this because I don't want to wait for 2 hours. But I can set it to any number I want. Often we'll just go ahead and punch in 3600. Let it run for an hour and see how it looks, or much longer. So it's a very straightforward configuration file. And if you download Bristlecone, there's examples included, and you can usually get this set up and actually run it in a few minutes. The output. One of the things that's really important is to be able to see this stuff graphically. So we had sort of a stat at doing a graphical output so that as this test is running, you're getting constant requests per second as well as response time. This test here was just something I ran on my Mac, so it's actually running against the local database. But you see it basically scaling up to doing about 80 requests per second. And then you can see the sort of ongoing query response time. And what this is doing is it's kind of bashing the database. You can see the response time sort of bouncing around. So this is pretty handy. It only shows 10 minutes, but as you're running the test, you can basically see what's happening and what your response time is. This is really nice if you're trying to diagnose a problem. So for example, you may have inconsistent response. When you start to see that in the graph, you can then sort of go in, like with HTOP and so on. Yes?
So even though it's running concurrently on 100 clients,
yes.
You have a graphic system that reflects the statistics of all these different clients.
Okay. Oh, okay. So really important. Okay, this is not distributed yet. This is one. Okay, really important point. I don't want to oversell this, but we're getting there. That's sort of the next step. The way that I should mention the implementation of this, I guess I should have had an architecture slide. I missed that. This is a big, fat Java client spawns threads. So now it turns out, that might sound kind of bad. You might think, hey, you can't generate enough load. Well, it turns out that this guy will go up to, I have a two-way Xenon that I use to run it's a Dell 1850. I use it to run a lot of the tests. I can go up to about 800 or 900 threads before the thing starts to choke, and before the test itself, the client itself becomes the bottleneck. The reason you can go pretty high is that it turns out that these clients are mostly waiting on the database. So they're mostly active on other machines, so the results works fairly effectively. One of the things long run we'd obviously like to be able to do is distribute this, have multiple clients, and then feed this stuff back. But this is all open source. If you guys want to get involved, you're welcome to help us do this. So that's an important point. Let me talk about the other tool that we have, which is called Benchmark, and it does the micro benchmarks. Again, it's in Java. Again, it's a single client. These things run what we call scenarios. So you code up a piece of Java code that just says, hey, I want to go test one very specific thing like inserting rows. It sounds kind of, it sounds like you couldn't possibly get that much information out of it, but it turns out that being very, very focused is important because it allows you to diagnose things and get specific costs. So these are you can make them as complicated as you want. Most of the ones that I write, and I've written about 8 of them that are available, it's a piece of code about this long, and maybe this long at most. It's really not very long. And then one of the things that we have, I'll show you in a second, is we have the ability to generate a cross product of parameters. So you can say, hey, I want to do it with 1, 2, 4, 8, 16 clients. We'll generate a cross product and basically run it all those different ways and allow you to compare. The scenarios, when they're run, they just spawn in separate threads, so you've got your multi-client testing implicitly built in. You can bound the scenario runs by iterations, like numbers, like say run it through 20,000 times, or run it for some number of seconds. We have some utility libraries, and we can generate 2 forms of useful output. We don't have graphics for this yet because they're kind of direction. So here's a configuration file. This one is actually easier. If you do Java, this is a Java properties file. And what I want to point out is the way that we do the cross products. So right here, I'm testing a cluster, and I'm testing a standalone database. So I have a couple of, I can include files. They contain my connection properties. Like where is this database, what logging do I use, so on and so forth. Then I have I'm going to run a test for 60 seconds. I'm going to try it with 1, 4, and 16 threads. And I just use the pipe symbol to say, I want to try these different combinations. And then for this one, let's see, it's a simple read. So it's basically just going to read all of the rows in this table. There's only one of them. And I'm going to try 4 different combinations. So if you do the math, you just multiply that out. There's 4 times 3 times 2. In this properties file, you get 24 test runs, each of which is 60 seconds in duration. So it allows you with very little setup to get a bunch of different runs. And what you then get, actually, first of all, I'll show you what you get in just a moment for the output. Let me talk about the benchmarks that we already have. We basically have specific scenarios to test things that are of interest to us. The first one is read latency. That's a big deal on whenever you have a proxy. So we have a simple one where we do simple reads of varying sizes. So for example, the one that I just showed you, basically you got a table, it's 100 lines, or 100 rows. You're just going to go and select out of those 100 rows as fast as you can. That doesn't do any work in the database, but of course if you have a proxy, the proxy needs to handle that. We also have a large version of that, which instead of reading one table, does a cross product on 2 tables. So if the tables are 100 lines long, bang, without generating really any effort on the part of the database, you all of a sudden get 10,000 rows back. That's really important. We do, for read scaling, we actually want to bang on the database a little bit more. We try and do CPU-intensive reads. I'll show you an example where we weren't totally successful with that. But we're going to do compute aggregates. In general, that's a good way to hit on databases. We also have something, I love buffer caches. So I wrote one where we basically do what I call an inverted keys scenario, where we have a secondary index on a big table. And that index is computed in such a way that if you read values sequentially like 1, 2, 3, they're all going to fall on different database pages. And that's kind of nice for forcing, trying to force the cache misses and things like that, and basically hit disk. Write latency and scaling. Inserts, it's amazing how much you can do with just with a humble insert statement. Updates that have sub-selects. Those are kind of nice if you have statement-based replication, so you have a kind of costly update because you have to do a lot of computation before you make the change. And then updates with complex query conditions where you're going to read something, get a result, and then do an update. That's pretty typical of transactions. We look for deadlocks, and then finally, thanks to our pals at Portabe, they have a TPC-B scenario that they have shipped me and I'm planning on adding to the doc. So these things take standard modifiers. You saw them in that configuration file, so I'm going to skip over those very quickly. And get to the output. So here's the HTML. If you do nothing else, you can basically get HTML output. This is kind of an eye test, but it's really, if it's on your computer, it's pretty easy to read. You basically see, this is a Postgres. I did a Postgres talk about 2.5 weeks ago, and so I'm still suffering from the after effects. But you basically see these things laid out simply in the order that they're executed. And so, for example, one of the numbers you get is the actual average operations per second. So how many of these operations did you have slammed through? And then you just have, you can look over, you can see what was running. This was something called PG pool, which is a proxy for Postgres. The number of iterations that you executed. It's all just laid out in a table. And if you're sort of an Excel weenie, at least I am, it's really in a state that's very, very simple to load into a pivot table and start to play games, do graphs, so on and so forth, and see what you really got. In the meantime, what I usually do is I run this, get the HTML output, see if it's worth looking at, because this costs me nothing to get, and then you basically can put it into Excel or your favorite spreadsheet to go from there. So let me show you some examples. These are meant to be suggestive. I'm working in an environment that's somewhat dirty. In fact, there's at least a couple of examples in this. But I'd like to just show you some of the kinds of results that you can get with this, and then I'll probably add I will add a few comments, just what I think these mean based on our experience with other testing. So a quick one is measuring mixed loads with evaluator. So you could ask the question, well, I ask this a lot because this is what we do. How does it compare to use a middleware cluster versus direct database access when I got 10% writes and 90% reads? So I'm going to use, in fact, exactly that evaluator file I just showed you a minute ago, that XML file. I could try different numbers of clients. I could try different weights on the queries. The test I'm going to show you was run on SC850. It was run a while ago, actually, but it just gives you a sense of what these things look like. This is sort of typical mixed query throughput. So what you have right here is on the low line. This is why it's nice to get these into Excel. You just do this graph, and so you have a standalone, which is processing about 150 queries per second. You have a cluster with 2 nodes, which is processing a little over 300. This is fairly good for read scaling if you see this, because you don't quite get a doubling. You obviously have some latency induced by your middleware solution. In fact, we'll explore that in just a minute. But you basically see a doubling in this slide. Another interesting slide is you often see when you're scaling up and you're distributing across multiple nodes, if you get things just right, you can get the database to really choke. And this is what you're seeing right here is the low line here. We're looking at query response. So what's our query response time? This is in milliseconds. We've got the 2 nodes which are receiving the updates and distributing them across the databases. You have a response time staying around 100 to 150 milliseconds. The standalone database is just as enough to put it over the edge. So we're competing. This particular test run, I believe again, it was CPU intensive, so what you're seeing is contention for CPU. It's just enough to really make the database.
And is it for the response time for any query, or is it like 95% trial medium?
No, it's actually, what we do is the aggregate of we basically have in the evaluator, it basically, each of the threads says, hey, here's how many queries of whatever kind I have done over the last 2-second interval. I think it reports every 2 seconds. So there's some stuff we could do to say, for example, let's see our insert rate.
What I'm asking here is the response time. Is it the average response time?
It's average response time, yes. Yeah, and one of the things we could do, I didn't smooth this because I think in this particular graph, the interesting thing that you're seeing here, and this is very common in overloaded databases, is very erratic response time. That's a classic sign of queuing effects where, around latches, for example. Another thing we can do is we can now sort of want to get precise. The question I often get is, and in fact, if you use MySQL proxy, the question you might ask yourself is, well, what's it costing me to go through this thing? So how much latency are we going to have? Every time you take an extra hop, there's going to be processing that's going to slow things down. So what we want to do is run queries of varying lengths, varying numbers of clients. An important thing for this kind of test So you want to make sure your data are in the buffer cache. And in fact, you basically want to have the database almost completely unloaded. Because what you're trying to measure is how fast are the proxies. So we have a scenario called read simple scenario. It does a sort of stupidly simple select, where it's just going to select everything out of the table. It's just going to do it again and again and again. So the database is just serving up data that's sitting there in memory. I ran these on a Dell SC 1425s, and here's some results. So I just recently switched to over to testing on MySQL 5.1. So this is a 5.1.23 build. I have to say, this thing seems to be a lot faster than 5.0. I don't know. Peter, do you guys have benchmark? We should talk about this later. Like InnoDB seems to be considerably better. So.
Which one 5.0 was 5.0 two very good to the old 5.0 was bad, but the rest of 5.0.
I've been testing both against 5.0.22 and then 5.0 I think 51.
Oh, 5.0.22 then.
Yeah, it was crap. In fact, I'll show you an example of that in a minute. Some numbers in there. So what you're seeing here is this proxy, the query throughput. Now, it's kind of interesting to look at the database performance, because in this particular case, the 5.1.23 basically is going to get up to, at 16 clients, which is what you see right here, it's pushing through about 10,000 queries per second. These are numbers per second. Then you do your comparison against your various proxies. So I've got three here. I've got the full unicluster product, which is our middleware. That pushes things through. It tops out at about 2,400 queries per second. We have our native client proxy. That's the fastest in this run. Tops out at about 3,300 queries per second. And then MySQL proxy, which looks like it's topping out at about 1,700 queries per second. This is kind of an interesting result. There used to be these big flame wars about Java versus C. MySQL proxy is written in C. Unicluster and MySQL are both written in Java. One interesting effect that I have seen is that, in general, well-written Java applications actually perform very, very well. And I think a key reason is they use cores more efficiently than many applications written in C or C++. And the reason for that is that you don't, a lot of the things like latching, sort of thread, sort of serialization around various objects, Java takes care of for you automatically and does good optimizations. If you're in a C application, you often have to do some hand coding to remove bottlenecks. So that, yes.
Do you do just partial queries, or do you?
Excuse me?
Do you do any kind of proxy, or is it just some pass-through?
These are basically pass-throughs. This is just, and in fact, let me show you the next number. One of the things that is, I just want to have in my head is can you get a number that just says what is the lowest possible cost for one query to move through a proxy? And that's what this test was designed to do, is checking query response as we, on each thread as we increase the number of clients. And so for one client on one thread, it's kind of interesting. The database will respond in 0.4 milliseconds. Our fastest proxy is 0.7. So you've got a 0.3 millisecond hit that you're going to take just by passing through the proxy. And that number seems, that's about as low as it gets. That's the lowest I've seen so far. And as you read across, as there's more and more load on this 4-core machine, you're going to see that the response times are going to go up. You get a kind of interesting effect here. For example, that these guys actually scale at somewhat different rates. The database scales very well. This just doesn't load it very heavily. MySQL proxy does a little bit better at the beginning, but then begins to scale rather poorly as it moves out. The Java stuff, and this may again be traced back to more effective usage of the cores, seems to scale better, at least out a certain distance. Yes.
And did you run in one box, or did you have like 3 nodes?
No, this was actually run on one box. So these are suggested. I want to be totally clear. These are suggested numbers. They're not definitive. And one of the things I'd like to do is begin we're at a point where this stuff is mature enough that we plan to publish some results that are more scientifically done. Yes, please.
One of the things, thank you for your response on how many people avoid it because people gather things out. Have you considered looking at the spread, looking at the one segment, see what the distributions are? I raise that because as we've done shown that sometimes these things will block out some of the users and they get very, very bad response.
Yes.
In.
Yes. Well, in fact, that's why I had that previous graph where I showed the response time bouncing around. That's exactly why I wanted to show that, because that's an effect we're very interested in. I would have shown you, to be totally honest, I would have shown you something on our own product. I was getting one of these effects, which I think was some unholy combination of two things running on the same machine. But that's exactly what we want to drill in on. We're looking for costs. We're looking for variation. We don't do anything specific to record variation. So, for example, this thing right here is just a number. There's no standard. We don't compute a standard deviation. But
that's an average as well, right?
It's an average, exactly. So
I think what in many cases was very often want to see 99, 95 percentile.
Yes.
Something like maybe 99.
Right. If you're at 99% off, you're at yes, please.
I was going to suggest a variation as seeing the median versus the average. Sometimes you should show the 95% percentile. We would also be very good that we had not been that.
Right.
Now, one of the questions to realize is just want to make sure the clients are running. You're ensuring that the clients themselves are running on a machine where they're not overloading.
Yeah. Really good. A very good question. So what I do when I run these tests is you have to watch this. I mean, all performance testing, it's a bit of an art. And so one of the things I typically do is I run top on my client machine, and I'm looking for, I want to make sure I don't see a lot of I/O weight. I want to make sure in particular that I see the processor idle, so I know that I'm not blocking. The most common thing is these clients will at some point just max out CPU time. And at that point, you're measuring the client response. So that it's no longer that's interesting.
And one thing I want to mention here about the MySQL proxy. MySQL proxy is event-driven single threaded. So the point here is that if you have any significant loads, then you would have multiple proxies.
Exactly. And that's an interesting, exactly. So I think that's one of the, on MySQL proxy, one of the things that I get out of this is that you obviously have to put it behind a load balancer. If it's not using cores efficiently, you're going to have to run multiple processes in the OS schedule.
Let me interest multiple ways.
Right. But these proxies are a very interesting subject. There's some interesting mathematics here that it's, if you're going to go into proxies, that's our business. It's important to look at that math quite carefully. So let me just say that is a great idea to do better reporting on the, sort of the things that you're bringing up. I think we kind of got the cross-product thing as the first thing we wanted to do to be able to, do the different combinations. I think.
And another thing, very nice graph you can do to measure response time is sometimes like plain graphs. Then you actually plot all the response time with graphs, and then you have different colors, and then you can see this is this distribution, there is there, that is there,
right.
Also is that is the most for example. That's very helpful.
One of the things I'd love to be able to graph. Actually, the most helpful is actually to see machine resources. So, for example, if I could plot CPU time on top.
That is also kind of very.
That's incredibly useful, and I've seen some very good plots. Let me show you another interesting result, and this is just another fact of life in the proxy business, is that it's actually not the cost of a single query that really kills you. It's the cost of rows coming back. So here again, got MySQL proxy, our MySQL connector, our unicluster product. And this just shows the performance. And I did a run just to check performance. I think I had just 10 clients doing this. And so you don't get, well, first of all, you don't get a great deal of throughput because what's happening in proxies is the more rows, most of the effort is just copying off the network coming in and back onto the network going out. So the more you have to do, the slower you're going to do, you're going to go. And the tail, the fall off is quite dramatic. So as you go from, in this one, you're getting a top unicluster gets 350 has throughput of 350 queries per second. That's actually still the best, but it dropped down to 5 per second by the time you're out to 10,000 rows coming back. Now, many applications here don't generate result sets like that, but this is really important to think about. In fact, I spent a good chunk of last fall dealing with this problem inside Unicluster, doing optimizations to at least get this up to some reasonable level. Read scaling. This is a good one. So basically, I mentioned we do the aggregates. This turns out to make this, to make a long story short, we just do this query right here. We do a select count star, which turns out to be well chosen for some databases, but kind of sucks for MySQL. So what I'm going to do is just show some quick graphs. What I want to do is answer the question, is when does the scaling out increase read capacity? At what point does a cluster do better? So let's have a look. So, for example, when we run this type of test, where we're aggregating across 200 rows, and as I say, just doing a select count, what happens is you see this kind of classic graph where the query at the beginning, Unicluster, which is your middleware solution, you're going through a big fat proxy that does the distribution of reads. It's slower because you're paying for latency, and you only have one client anyway, so that's the maximum payment. The more load you put on the system, the better the proxy gets. So at some point, the database, as you can see, at 4 cores, it's kind of interesting, this tops out. At 4 threads, the database basically starts to plateau. It was on a 4-core machine, that may or may not be related. And then you see the middleware continuing to rise so that until it gets 2,500 queries per second. Interesting thing, this isn't really what I expected. I was expecting to see more or less double the performance at the top, but it turns out that MySQL just does count star pretty quickly. There's some optimizations built in. However, if you run this on other databases, like Postgres, this is run on Postgres 8.3, you see a very different pattern. It turns out that selecting counts is quite slow. So here, the database really never gets up. This is done on exactly the same machine, exactly the same hardware, and the same software you're proxying. The database only gets up to about 900 queries per second. And you get this nice graph that shows the middleware getting double the performance at the top.
How many clients?
Yes. The clients here are marked on the bottom. Sorry about that. So I just basically 1, 2, 4. I just do powers of 2. So they flatten out.
What's that 50 number you have at the bottom?
Oh, 50. That is that's 50 rows. This is just an artifact of Excel. I'm stripping out other rows. Please.
On the previous graph, what entered the previous?
Thank you. InnoDB for everything. And actually, I've done MySQL before. This is when I want to start publishing some of these things. We'll do it on we're thinking about doing it on our website. MySQL just rips on some of these tests. It's amazing. Like for inserts, you get, on really basic equipment, I get about 7,000 inserts per second on InnoDB. I get something like 14 or 15,000 sometimes on MySQL. It's double the rate. Very, very fast. Queries very fast.
But as the number of clients goes up, though.
Yes, then you would expect to see some tail off. Practically quite a bit. Yes?
When you do queries, are you doing queries on primary keys?
Well, it depends on what I'm doing. If I'm just doing a latency test, which is, these guys right here aren't using keys because we're just trying to load the database. But it depends on what we're testing. Yeah, sometimes I do primary keys, sometimes I don't.
Yeah, because InnoDB does cluster primary keys, so the queries will be a lot faster with a key.
Yeah, and in fact, most of these scenarios are not all that dependent on primary keys. They're really just trying to put load on the database. And sometimes I do less efficient queries. And it comes back to this issue about not having a distributed, because I'm going off a single client, I have to do somewhat artificial things to make the database work a little harder. Let's see, I think we've got 5 more minutes, so I'm going to push through because I got some interesting ones on replication latency I'd like to show you. So, big question. How does replication affect master performance and what is the latency per se? This is a big question in the MySQL world. And it's one that's interested us interested me personally for a long time. So, we're going to go ahead and use the humble insert. But what we're going to do is we'll test varying numbers of clients, and then the way that this test works is it inserts in one database, and then it does a primary key lookup on another database. So, and basically, if you're testing the standalone database, you insert the row and then look it up, and that gives you your baseline. If you're replicating, you insert the row and then you look it up on the other side and see how long it takes to get over. And that gives you kind of a rough and ready idea of what your latency is. So the first thing I did was actually just ran the straight test. All I'm doing here is checking the master overhead. So this is using 5123. It's on InnoDB. It is, thanks to Peter, it is correctly configured. So I'm actually not flushing. I'm just flushing out to the file system. I forget the name of the property for that. It's pretty long, and the settings too. But basically, when InnoDB is correctly configured, you get performance that looks somewhat like this. So basically, what you're seeing, this is just looking at the master and how fast we can push inserts through. We basically can get up to five clients. We top out at around 7,000 inserts per second. It's pretty quick. And then when I turned replication on, basically what I did was I have the replication set up. So in one case, I picked the database to replicate it. So I go to a non-replicated database. When I switch over and go to a replicated database, I get 5,000 inserts per second. Yes?
Now, you may have already asked the previous person, but if you turn off all indices first, then do the instruments and rebuild the index, what's the total time for that?
I didn't test it. So, no, I don't know. That's
the rate that is, you know, performance of other databases recommended in the past is a lot of inserts.
Right.
And the right way to do it is kill all the indices, do the inserts, and rebuild the indices.
Right. What I'm really doing here is looking. So, you know, I did the master slave design. The key point is how fast can things get pushed through your master? And one of the things is that MySQL is actually relatively performant. The masters there's not as much of a load on the masters as there is on other systems. So you're going from 7,000 down to 5,000. If you compare the competition, exact same hardware, using Postgres, first of all, Postgres doesn't get as much, it tops out about 4,000 inserts per second on exactly the same hardware and disks, same number of cores. It also has much higher overhead. And part of the reason for this is that Postgres is trigger-based, and well, at least I believe this is part of the reason. So it does a little bit more work when it's logging the stuff that's going to get replicated. So this is a good example. If you're running Postgres, in this particular case, you're going to, at 20 clients banging away, you're basically cutting your master performance down by half.
And
yes, sir. Yes. Just using one right now. I need to. No, that's a really good question because that's going to put more load on the master and other things.
I think one good question here is when you speak about compare master with a standalone server, are you speaking about just connecting the slave, or are you speaking about enabling the binary log?
I'm sorry, say that again?
Well, when you compare it to the MySQL, then you say,
Right.
okay, I compare MySQL and MySQL with replication.
Right.
So are you just having MySQL do binary log and then MySQL do binary log and slave, or you're comparing MySQL without binary log to MySQL with binary log and slave?
Okay, so for master overhead, what I did was MySQL, it has the binary log turned on, but I'm not going to databases being logged, so that may not be a totally fair test.
Yeah, because my point here is that the binary log is not just self-verification. If
Right.
you care about the data, you have to use it for to get point time recovery. So.
Right. No, that's a good point. So I should in fact say, hey, I'm going to take this cost. It's something.
Yeah, I mean, and I think it's very interesting to see what overhead comes from just maintaining the binary log,
Right.
and what overhead comes from having a slave. Because I think what most overhead comes from having binary log enabled, not from
Right.
having a slave.
Exactly. No, in fact, that's exactly in fact, that test was just really just the effect of writing the binary log. It's as simple as that.
So in this case, to summarize, you have binary log turned off for the standalone?
No, for the standalone, the binary log is turned on, but I'm not going to a database
Okay.
that's replicated.
So this is
so I'm not writing to it.
Okay.
So you mean you have to replicate the binlog DB component, or?
I'm using the parameters to select databases for replication. So I have only one database.
So
selected.
basically, events do not written to line at all,
They're
right?
not written to the binary.
Okay.
That's exactly what it is. Because I want to have something where I can just switch back and forth.
Okay.
It'd be more scientific to set up two different servers. Let me just show you the replication latency. This is actually kind of interesting. There is one of these little things you get in performance testing where at one point on this graph it appears that the slave gets stuff faster than MySQL gets it itself. That's something must have happened during that run. But basically what you're seeing here is if I do one run where I just put the thing in and then check to see whether it's on the current database, I do another run where I actually put it in and then I check to see how fast it got to the slave. So the interesting thing is the latency is actually pretty good. MySQL, in fact, this has been my experience over like a year and a half or so looking at this. MySQL actually has relatively low latency between masters and slaves if you don't have too many slaves. But I think we're running out of time here, so what I'm going to do is I'll just show you one last thing, which is if you don't get replication configured right, you can really screw yourself. Here's an example of this. Using InnoDB, I'm on MySQL 5.0.22. This is just something I ran a while back. And I was just using the default InnoDB settings, which really suck. Basically what they do is they cause you to lose group communication when you have the bin log enabled. And you get results, which is a really interesting result. In fact, I didn't know what was going on when this happened, but I figured it was group communication. You have, with one client, you get about 600 inserts running through per second. With 10 clients, you only get about 1,000. And so what you're basically doing is you're getting serialization effects here. And in fact, when you do setup replication, it's very important to pay attention to the performance, to the configuration settings on your server as well as your operating system. Otherwise, you get stuff like that.
So what was the setting?
Let's say Peter told it to me. The value is 2. The setting is about this one.
Okay.
There you go. Equals 2 is your friend, but then make sure you're only flushing to the file system cache. You have to make sure you have a RAID or battery backup or some other sort of data. So there's more stuff I could probably talk about this all day, but thank you very much. Let me just say one thing about this. You can get this software. So we're doing a stack for Scaleout. That's a big reason why we're after this problem, why it's so interesting to us. We have these bristlecone test tools. You can visit us. You can get bristlecone straight off www.continuent.org. Come visit us at our commercial site. This is all open source. It's GPL v2. If you're interested in it, you'd like to contribute, let me know, because this is a fun problem. I'd love to have more people working on it. So thank you very much. Thanks.